Okay, hi everyone. We're going to get started in just a few minutes.
Do you want to tell them to accept breakout rooms?
And just as a reminder, please accept your breakout room invitations as you get them, just so that we can get everyone into rooms quickly.
Did you put the slides up?
No. Because they have the answers in them. About how many people are on Zoom?
I don't know because they're all in breakout rooms. But there are 57 on.
So we got some questions in the chat about acceptable formats for your homework to be uploaded in. So you don't have to print out the sheet we gave you and fill in the answers. Feel free just to use a piece of paper and write it out, and then take a picture of that and upload it. Yeah, we realize not everyone has printers right now, so that's totally fine. We're happy to work with any format that you'll give us. Once again, everything isn't graded. We're just going to give some qualitative feedback. And that'll start this weekend. We'll start going through all of the homework that you guys have turned in already. And then for large issues, if the whole class was confused about a certain problem, then we'll send out an announcement to clarify, just because, yeah, then there was an issue with the question on our end.
You should already have gotten feedback on homework 1 if you turned it in.
Okay, great. So now we're going to go ahead and get started for today. Today we're going to discuss a lot about nomenclature. So this is basically going to be a lot of definitions, and we don't expect everyone to memorize all of these details. In fact, we're only going to discuss some of the details today, and a lot of it is just something that you'll learn in 1A and really probably never be expected to memorize, just because some of these naming things get very, very complicated fast. So many chemicals have a common name, but then all of them have a proper name that's been given by the International Union of Pure and Applied Chemistry. So you'll see that name thrown around, IUPAC. So all of the naming conventions come from them. So they're sort of the official source of all of the naming rules. But today we're just going to go over some of a general overview. So first, we'll talk about naming monoatomic cations. So monoatomic ions contain just one kind of ion. So this is the simplest case of naming ions we can look at. So all you do for naming a monoatomic cation is you basically add ion to the end of the regular name. So example for sodium, you have sodium plus, and you would just call that a sodium ion. So that's pretty straightforward. But things can get a bit complicated if you don't know what charge the metal is. So yesterday we showed you that periodic table. So some of those cations will always have the same charge, but for some of them, especially transition metals, you don't necessarily always know the charge of the metal. And actually, this is always written on many periodic tables. So you'll just see in the top corner, usually a +2 and a +3, for example, to say that that metal can exist in the +2 or +3 state. So this isn't something that we expect you to be able to know off the top of your head. I can't even go through all of the metals and tell you if it would be a +2 or a +3. But we do expect you to be able to look and read it off of a periodic table if that information is provided on that periodic table. Does that kind of make sense? Feel free to post questions in the chat. We'll get into some of this chemistry a bit later, but for right now we just want to quickly define oxidation number and simply how it applies to naming. Okay, So if the element can form more than one kind of cation, then we need to add the oxidation number in parentheses immediately after the name. So the oxidation number in this case is just a fancy word for the charge of the ion. So for example, the oxidation number of sodium plus is just 1, right? Because sodium has a +1 charge. And we always write this in Roman numerals just as a convention. So here's one more complicated example of a metal that can actually have two different charges on it. So copper can actually exist as a +1 or as a +2 cation. So then if it was +1, you would write copper, then you'd have your parentheses and you'd put a 1 Roman numeral inside. If it's copper 2+, you'd have, you'd instead use the Roman numeral for 2 after copper. So once you know what charge it can be, the naming is pretty simple, and we want you guys just to focus on how this relates to naming right now. Okay. So for naming monoatomic anions, you simply replace the ending of the name of the element with "ide." So for example, if you have bromine, Br-, you would just simply call that bromide. And then things get a bit more complicated when you have polyatomic ions. So these don't always follow normal rules or patterns. So this is a table I found where they go through some of the names of common ions. So I suggest that you guys kind of read over this table and familiarize yourselves generally with what these names are, just so that if someone is like, hey, this is a permanganate compound, that you kind of know where to go and look up that information if you don't know that off the top of your head. Again, we don't expect you to go out and memorize hundreds and hundreds of names, but these are some of the most common ones. So if you're going to commit anything to memory, these probably would be the ones to do. Okay. So all of that was about naming specific cations or anions, and now we're going to discuss how to name ionic compounds. So ionic compounds contain both an anion and a cation. So in order to name these compounds, we always first write the name of the cation, followed by the name of the anion. But we always omit ion from the name, right? So if you remember that we called the sodium ion a sodium ion, when you write out the name, you wouldn't write ion, right? And the numbers of anions and cations in the compound don't affect the name at all. So for example, if you have sodium chloride, the ion names are, for the cation, sodium ion, and for the anion, chloride. So the name of the ionic compound would be sodium chloride. And when we write formulas of ionic compounds, this is a bit of a review from yesterday. We would just simply write them as the numbers of different atoms in that compound. So for example, again, if you have sodium chloride, you'd have your sodium ion and your chlorine ion. And down here at the bottom, I just put an example of how you would use a charge balance to help determine how many cations and anions you have. So since sodium is a +1 cation and chlorine is a -1 anion, and we know that the overall compound has to have a net neutral charge, we know that there must be 1 sodium and 1 chlorine in this compound. But for example, as you saw in your homework last night, this can get more complicated when you have +2 and a mixture of -1 and things like that. So I just wanted to quickly show how you could use a charge balance to determine and write out the overall formula. Okay, so now in your breakout rooms, if you could just take 2 or 3 minutes and write out the names of these compounds. And as a hint for the bottom one, think about, can cobalt have multiple oxidation states? And then, you can look up a periodic table that may have that information on the internet as well. But you should also be able to determine the oxidation state just from the formula itself. So I'll give you a few minutes to do that, but feel free to post questions in the chat as well. Does anyone need more time? Just post in the group chat if you need more time, or the live chat if you need more time, and then we can wait a few more minutes. Yeah, so let's go back and review that. So an oxidation state is another word for oxidation number. So that's basically asking what's the charge of cobalt? So is it +1, +2, +3? Because then you would need to write that number in parentheses after the metal. Does that make more sense? Okay, does anyone need more time? Okay, great. I'll wait about like 20 more seconds for the lag, but otherwise then we're gonna go on. Okay, great. So the first one would just be potassium bromide. So the cation is a potassium ion, and the bromine is a bromide anion. So you would just put them together in this case. So the second example is a bit more complicated. So we know that there are two chlorides, and then each chloride must have a -1 charge. So that's a good hint, because we know that the overall compound must have a total charge of 0. So that means that the only way for this compound to be neutral and have a charge of 0 is if we had a cobalt-2 ion. So that means that the cobalt must have a charge of +2. So then you would have to write cobalt, then have the parentheses and the 2 at the end. So this is one example if we wouldn't expect you to just know off the top of your head that cobalt can have multiple charges. Because it's a transition metal, that's a good sign that this may happen, but we just expect you to go and see on the periodic table or look it up to learn that information. So again, we don't expect you to go through and memorize the different charges of every single element on the periodic table. So the name of this compound would just be cobalt-2 chloride. So now we're going to move on to naming of inorganic compounds. So in this, I don't see anything in the group.
It says, how does bromine become bromide?
Oh, okay. Yeah, so if we go back to the beginning when we talked about monoatomic anions, that whenever you're naming an anion, you just replace the ine, the I-N-E, with ide. So you just kind of remove the last few letters of every single name and just add an ide. Okay, and then the next question, why does chlorine have a negative charge? So if you remember back to our lesson yesterday, we talked about cations, anions, and valence electrons. So chlorine is in the row where they have 7 valence electrons. So that means that they get significantly more stable if they take 1 more electron, so that they have 8 electrons in their valence shell, because that would give them a full valence shell and that's the most stable configuration. So that means that chlorine wants to have a -1 charge, so when we go to form ionic compounds, we'll get a Cl minus. Yeah, that's a great question. We can talk more afterwards about that because some of that information was also on homework for last night too. And yeah, then you would, for a charge balance, you would just cross multiply. So then you know that if you need a total charge of 0 and you have a charge of 2 minus, that you must have +2 charge. So you can just write it out as an algebraic equation, and then it can make a lot more sense. Why does cobalt have 2+? Do you mean like why is it +2 in this example, or just in general? Yeah, so in this example, cobalt has a +2 charge because we know that there is a -2 charge for the 2 chlorine anions. So chlorine will always only be a -1 anion. It can't have any other charge. So then we know that if we say we have 2 negative charges from those 2 chlorine ions, that to get a total charge of 0 for the entire compound, that cobalt must have a +2 charge. And yeah, so for naming compounds, by convention, the cation always goes first. Yeah, and all of these things you'll get used to over time with practice, and then it'll just kind of become habit. But we don't expect you to have to memorize all of this information instantly, of course. Okay, I'll give another minute for any questions about this before we move on to other types of compounds. Cool, so I'm going to go on to naming of inorganic compounds. So in the conventions for this, we want to name the element that occurs furthest to the right on the periodic table second and add the ending "-ide" to it. So in order to do this, it's probably helpful if you pull up a periodic table on your computer as well, because again, we don't expect anyone to know all of the positions of all of the elements on the periodic table, right? But that is the convention, that you would have the element that occurs farthest to the right would always be named second, and that's the one that you would just add "-ide" to the ending of. And then for this, you would also want to use prefixes in front of the element names to show the number of atoms in each compound. So here is a table of the different prefixes used. So you have mono for 1, di for 2, tri for 3, and it goes on and on. So these prefixes you should probably commit to memory, just because that will make everything a lot easier. And here is one example. So you have N2O3. So there are 2 nitrogen atoms. So you would use the prefix di in front of nitrogen. So it would be dinitrogen. And then you have 3 oxygen atoms. So you would use the prefix tri. And then because that is the element that comes at the end, you would also take away the en part and write oxide. So then you would get dinitrogen trioxide. Okay, so here are a few quick naming examples. So just in your groups, please take a few minutes to name these. And again, feel free to pull up a periodic table on the side to help. And then if anyone wants me to go back to the previous slide that gives the name of the prefixes, just let me know, and I can click back. But hopefully 1, 2, and 3 are all pretty simple. I just went back a slide so that you guys could see the prefixes, but I will also type them out. Okay, does anyone need more time? If not, we'll go ahead and get started in 30 seconds. Okay, so someone asked, does it matter which element goes first if they're both anions? Do you mean, so two?
N and O, if they were ions, would both be anions, but this is...
Right, yeah, so inorganic compounds are different from ionic compounds. So all of the naming conventions we discussed before were all related to ionic compounds. Ionic compounds, if we think back to last class, they all have these different type of bonds where they're kind of stealing electrons from each other, and it's all based on electrostatics. So that means that you have anions and cations together. So now we're thinking about inorganic compounds. So inorganic compounds, they all have covalent bonds, so they're all sharing electrons. So you can't really think of this as like a nitrogen that's negative and an oxygen that's negative. That's not true. The bonding is very different, so that doesn't happen. So that's why the naming is so different, is because these aren't ionic compounds. These are a completely different class of compounds called inorganic compounds. So I don't know why they picked the rules the way they did, but this is the convention just for inorganic compounds, which are different from ionic compounds. So then which element comes first and second in this case is determined by where it is on the periodic table, which is why it may be helpful for this example if you open up a periodic table on your computer too. Okay, so since no one wanted more time, we're going to go ahead and review the answers. So the first one would be called phosphorus trichloride. So chlorine is farther to the right on the periodic table than phosphorus, so that's why it goes last, and that's why we add the "ide" ending to the end. And then because there's three, we use the prefix tri. So the second example is dinitrogen oxide. So in this case, there are two nitrogen atoms and there's one oxygen atom. So then we use the prefixes di, and then we don't use a prefix if there's just one in this case. Okay, great. So any more questions about inorganic compounds? Because then we're going to move on to organic compounds next. So you would add the mono prefix if it's the element that comes first, And then if it's the element that comes to the end, you would just leave it out. That's the convention. Okay, so it doesn't look like there's any more questions. What exactly are organic compounds? Yeah, this is a great question. So organic compounds all contain carbon. So that's what separates them from inorganic compounds, is that organic compounds just contain like carbons, hydrogens, oxygens, and nitrogens. Whereas inorganic compounds often contain metals. So if you think back to the regions of the periodic table that we defined, inorganic compounds often have like transition metals in them, things like that, or they don't have carbon often. Whereas organic compounds are all based on carbons. Yeah, so if anyone's confused about the difference between ionic compounds, inorganic compounds, and organic compounds, definitely post in the chat or come and talk to us afterwards, because you do need to know the difference in order to name things correctly. But we hope that last class and this class that we're able to kind of make those distinctions. Yeah, so some inorganic compounds have carbon, but so maybe the better way of thinking about it is organic compounds don't have metals. So they're just carbons and hydrogens and things like that. Whereas inorganic compounds could have like cobalt in them, and then sometimes they'll have some carbons, but they always have a metal. Yeah, so ionic compounds are based off of ionic bonds, right? So last class, we learned about the difference between ionic and covalent bonds. So ionic compounds are the ones that are going to form those ionic bonds, whereas inorganic compounds and organic compounds all have covalent bonds. So that's a good way of separating it. Yeah, so bonding can get pretty complicated. You can't actually strictly define ionic bonds or covalent bonds. For example, if you could say that a bond is covalent but has a lot of ionic character. So all of this will be discussed in 1A because it actually gets pretty complicated. And bonding is something we could spend like 3 weeks talking about just on its own. But for right now, let's think of ionic compounds as having ionic bonds, and then organic and inorganic compounds, those all have covalent bonds, just because that will help us think about why we are naming the things the way we are. Great. Okay, so I'll wait another 30 seconds for more questions, and otherwise I'll move on. Great, okay, let's move on to naming organic compounds. So once again, these are the molecules that contain all of the carbons and hydrogens. So naming organic compounds is very complicated, so we're just going to look at one set of organic compounds called hydrocarbons right now. So those are the compounds that contain only carbon and hydrogen. So in this cases, we would also use Greek prefixes to indicate the number of carbon atoms in each hydrocarbon. Yeah, so just to emphasize that again, the prefixes only apply to the number of carbon atoms. So we're not going to have a prefix for the number of hydrogens, just the number of carbons. And then we can also use a suffix to indicate if the hydrocarbon has a single, double, or triple bond. So we talked about this a bit last class, but just to review, this is what a single bond looks like at top. So that's what you would call an alkane. So the ane is a suffix in this case. And then if you have a double bond, so that's represented with 2 lines between the carbons, that would use a suffix ene. And then if you have a triple bond, which would be represented just with 3 lines between the carbons, that you would use a suffix yne. So all of these are underlined in this example. But so those are a few general rules to know about in naming hydrocarbons. And then there's also a lot of functional groups that come up in organic chemistry. So each of these functional groups are groups of atoms within a compound that have characteristic properties. So they're pretty important when we think about reactivity and how these molecules behave. So because they're so important, we give them separate names. So these are some examples of different functional groups that occur in molecules. So these are by far the most common ones. So it's probably good to familiarize yourself with these so that you can kind of know off the top of your head sort of what a carboxylic acid looks like, for example. Or if someone says an alcohol, you know that means there's an oxygen bonded to a hydrogen, just because that can save some time later on. But again, we don't expect you to be a dictionary of different names, but these are some really good common ones that you definitely want to familiarize yourself with. Okay, so now just take a quick break. We're going to move on to moles and molecular formula determination. So if there's still more questions about ionic and organic nomenclature or how they're named, please post in the chat. So I'll just give you guys 2 minutes to digest that and then ask more questions. Someone asked to go 2 slides back, so I think that's the slide about the different types of bonding. If it's the wrong one, just let me know. Okay, someone asked, can I go back to naming monatomic anions? Yes.
Also, all of these slides are posted on B courses, so you're also welcome to download those.
Yeah.
The ones that are on B courses today do include the answers to the discussion questions, so don't go ahead.
Yeah. Yeah, so there's also a lot of resources and tables of all of this stuff online too. So there's like multiple ways to kind of organize this material. Okay, so now let me go back to the other slide that. Okay, so I think this is what someone had wanted to go back to. Yeah, so these prefixes probably are really important to memorize just because they're going to come up a lot. And if someone's talking, if like a professor is talking in class about like, oh, we have this like tetranuclear compound, it's good to be able to just know that they mean like 4, just because otherwise it can get confusing in chemistry because there's a lot of big words for a lot of things. So it's nice to just know off the top of your head, like, oh, they said a thiol, I know there's a sulfur in it. And you don't need to know much more than that, but it's good just to have in your mind kind of what some of these things mean. Yeah, I've never had in chemistry anyone make me name really ridiculous organic or inorganic compounds. It's always more of a qualitative thing. So hopefully you guys will have a similar experience. Hopefully. Okay, it doesn't look like there's more questions, so I'm going to move on to the rest of lecture today. So we wanted to quickly go over what moles are. So moles are the SI unit for amount of substance. So they're used in chemistry to report the number of atoms, the number of ions, and the number of molecules. So they're just generally the unit we use for amount of things, or more professionally, the amount of substance. So the reason we need to do that in chemistry is because atoms are so small. So if we can actually observe, like if you actually are weighing out some amount of carbon, there's just like 10 to the 26 number of atoms for you to actually be able to see it with your eyes. So that's why we use moles, is to kind of put it at a level where we can actually think about it in chemistry. So by definition, 1 mole of objects contains the same number of objects as there are atoms in exactly 12 grams of carbon-12. So you may wonder why carbon-12? Just goes back when they defined what a mole was a while ago, carbon was one of the most important elements. So this is a little bit arbitrary. They could have done this for any element. So this definition isn't super important, just as long as you know that moles are used to report these numbers of atoms, ions, and molecules. But that is the formal definition of what a mole is. Okay. And Avogadro's number is the unit we use to convert moles to number of objects. So this was defined based on carbon-12, like what I discussed last slide. So someone measured this and they found that there's 6.022 times 10 to the 23rd atoms per mole in carbon-12. So now this is the ratio we use when we convert any number of objects to moles in chemistry. So this is something that's definitely really worth committing to memory, just knowing that 6.022 times 10 to 23rd objects per mole is Avogadro's number. Okay. So the molar mass is the mass per moles of particle. So the molar mass of an element is just the mass per mole of its atoms. And the molar mass of an entire compound is the mass per mole of all of its molecules. So you would have to add up the mass of all of the carbons, all of the hydrogens, and all of the other elements in that compound to get the total molar mass of that compound. Whereas for an element, you would just find the molar mass of that one thing. So now let's do a quick example of how to calculate this. So in your breakout rooms, can you calculate the amount or number of fluorine atoms in 22.5 grams of fluorine? So on the slide, I included Avogadro's number for reference, but you may also need to look up a periodic table to find some information as well to help solve this problem. So feel free to do that on your computer. Okay, does anyone need more time? If not, we'll go ahead and start in a minute. Okay, someone said more time, so I'll give you guys another 2 minutes. Have you all been able to find the information you needed from the periodic table online? Okay, does anyone need more time still? If not, we'll go ahead and get started. Okay, great. So let's go ahead and review this. So in this case, you would take your 22.5 grams of fluorine and you would convert that to moles of fluorine. So to do that, you would use the molecular weight of fluorine, which you can find on the periodic table. So if you think back to what we did on day 3, when you have those boxes of the periodic table, they always have the average mass of each element printed at the bottom. So that's where you'd have to get this information. And then to get the number of fluorine atoms, you would take the number of moles, 1.18, and then you would multiply that by Avogadro's number. So this, again, you can think of as a unit conversion, right? So you have moles and you need to convert it to number of atoms. And to do that, you multiply by this ratio called Avogadro's number, which is 6.022 times 10 to the 23rd. So that's the number of atoms per mole. So then in this case, you would get 7.11 times 10 to the 23 fluorine atoms. Okay, great. So let's move on to chemical formulas. So there's 2 different kinds of chemical formulas you can have. So one is called the molecular formula. This shows the actual number of atoms of an element in the molecule. And then you can also have the empirical formula. This shows the relative number of atoms of each element present in the compound. So let's quickly go through glucose as an example to see what these mean. So for the molecular formula, again, this shows the actual number of atoms. So to find the molecular formula, you would just need to count how many oxygens, how many carbons, and how many hydrogens are actually found in that molecule. So one good way I found to do this is to just draw it out, so then you can go and easily count how many of each type of atom you have. So example for carbon, as we learned yesterday, carbons are often represented just as these points on lines. So here I've gone through and I've numbered all of the carbons present in glucose. So there are 6 carbon atoms in glucose. We can do the same thing for hydrogen. So there's 5 hydrogens that they actually bothered to write on here. But then, as we know from class yesterday, they kind of assume that you know that there's hydrogens everywhere else. So there's a 6th and a 7th hydrogen right over here, because right now that carbon only has 2 bonds shown, and you know that a carbon must have 4. So there's 2 extra hydrogens that aren't shown. And then you can go through and do that for the rest of the molecule and find all of the hidden hydrogens that weren't actually written out. And you would get a total of 12 hydrogen atoms in glucose. And then you can also just count out the number of oxygen atoms. So in this case, you would get 6 oxygen atoms. So that would give you a molecular formula of C6H12O6. And then to convert this to the empirical formula, what you would want to do is just normalize this by the lowest number. So you would want to divide 6 by 6, 12 by 6, and 6 by 6. Because an empirical formula is just asking for the relative number of each atoms in a compound. It's not asking for how many exactly are there. So then we could write the empirical formula for glucose as CH2O. So it's convention that you always want the lowest subscript to be a 1. So you wouldn't want to write C2H4O2. You would want to write CH2O. So if anyone has questions about some of the nuances of this definition, please post in the chat and I can answer those. Otherwise, we're going to move on to some other examples. Okay. Yeah, so it's just like simplifying a fraction. So basically, it's just easier to have a 1 everywhere, so the convention is to just do that. But it's exactly like simplifying a fraction. That's a great way of thinking about it. Okay, so and then in chemistry, we often need to think about mass percentage. So this is the percent mass of an element relative to the mass of a compound. And often you'll see in textbooks just write this as 40% carbon. What that actually means is 40 weight percent carbon. So that's why it's a mass percentage. But they often omit the weight part because it's kind of assumed. But in this class, we'll try to go through and actually write weight percent. So this is denoted just by WT percent instead of just a percentage sign. But just be aware that, at least I've seen in the textbook you're going to use for Chem 1A, that they kind of just assume that you realize it's a mass percentage. But try to always write weight percent just to denote this. So the mass percentage of an element is defined as the mass of element in that sample divided by the total mass of the sample. And then you would multiply by 100% just to put that in terms of percent instead of as a decimal. So hopefully some of this has been seen before. Okay, so then how would you actually determine the empirical formula? Like say you were given or you experimentally measured the weight percent of carbon, hydrogen, and oxygen in a compound. How would you actually go about determining the empirical formula? So to do that, you would do these 4 steps. So first, you would assume a base calculation on 100 grams of compound. So you may wonder why 100? Just because 100 is really easy to work with, but you could pick whatever base you want. It's just 100 is the easiest, so that's why we're going to use that. But if you find it easier to use 1, please go ahead and do so. So then once you make this assumption, you would go through and you would determine the number of moles of each element in 100 grams of the total compound. And then you would divide each value of moles by the smallest of the values. So again, this is just like simplifying a fraction. And then you would multiply all of these numbers by an integer to get whole numbers if for some reason you got that you had 1.3 carbon atoms, for example. So this is a lot of words we're going to go through together in class and do an example. So let's consider adipic acid. So we measured this and we found that there was 49.32 weight percent carbon, 43.84 weight percent oxygen, and 6.85 weight percent hydrogen. So how would you find the empirical formula? So step 1, you would want to assume that you have 100 grams of a compound. So you can calculate the grams of carbon by multiplying the weight percent of carbon times 100 grams. So this would mean that in this case, you had 49.32 grams of carbon. And then you would go through and you would do this for oxygen, hydrogen too. So this basically just makes it easier to work with these numbers instead of the small decimals points. Okay. So now that we have the number of grams, we would convert to moles. So this, you would just use the molar mass from the periodic table and you would convert the number of grams of carbon, oxygen, hydrogen just to the number of moles. So that's what I did here. Again, this is great practice in unit conversion to actually write out the entire fraction just so that you can cancel out all of those units and make sure that your dimensions are all correct, just like we talked about earlier in the week. So then in this case, you would get like 4.1 moles of carbon, 2.7 moles of oxygen, and 6.8 moles of hydrogen. So then you would want to simplify this by dividing each value by the smallest value. So in this case, that's the number of moles of oxygen. So we would go through and we would divide all of these numbers by the number of moles of oxygen. So that would give us 1.5 carbons, 1 oxygen, and 2.5 hydrogens. So right now, this is basically we've just determined the ratio of carbon to oxygen to hydrogen, which is what we need to get the empirical formula. And then because we, by convention, don't want to report these decimal values in our empirical formula, we would just multiply everything by 2 to get whole numbers. So you would get now 3 carbons, 2 oxygens, and 5 hydrogens. And that would be your empirical formula. So now let's talk about how you would get a molecular formula. So first, you would find the mass of the compound from the empirical formula. So this means that you would have to find the empirical formula first, which can be some extra work. And then you would divide the molecular mass of the compound by the mass given by the empirical formula. Then you would multiply the empirical formula by this number to get the molecular formula as a check. So let's go through the same example of adipic acid that we did for the empirical formula, just to go through this so it's a bit clearer. Okay, so this is the same example for adipic acid. We've determined that the molecular formula is C3H5O2, and then the information that you'd have to be given to be able to solve this problem is the molecular mass of adipic acid. So this is 146 grams per mole. So this would always be given to you in a problem because otherwise you wouldn't be able to solve the problem. So now we can ask, what is the molecular formula? So first step, you would want to find the mass given by the empirical formula of C3H5O2. So to do that, you would just go through and multiply basically all of these numbers by the mass of carbon, the mass of hydrogen, and the mass of oxygen. So then you would get 73.08 grams. And then you would want to divide the molecular mass by the mass given by the empirical formula. So this would be 146 grams divided by 73 grams. So this equals 2. So I did round a bit, and that's okay. It's okay to round to the nearest whole number in this case. So that means to find the actual molecular formula, we would just go through and multiply the empirical formula by 2. So that means instead of 3 carbon atoms, you would have 6 carbon atoms. And instead of 5 hydrogen atoms, we would have 10. And similarly for oxygen, we would have 4 oxygen atoms. So that was a lot of math. So I'll give you guys some time to ask questions about this example. But there's also a lot of practice on the homework, and it's best just to be able to go through and kind of do some of these things on paper to get used to it. No questions at all? Give it another minute. Why did I choose to multiply by 2? Okay, great question. So basically the easiest way to look at this, maybe if we go back to the glucose example, So basically we just need to find the ratio between the empirical formula and the molecular formula. So if you look at the empirical formula for glucose, you would need to multiply all of those by 6 to get the number of actual atoms in the molecule. So we're just trying to find the ratio between the empirical formula and the molecular formula. And the easiest way to do that is to use mass. So given the mass of a molecular formula, as long as you can find the mass of the empirical formula, then you should be able to divide those two numbers and find that ratio. So that's why our strategy is first finding the mass of the empirical formula, then finding the ratio of masses between the empirical and molecular formula, and then using that number to multiply through to get the actual formula. So hopefully with this picture it makes a bit more sense. Okay, great. So this was all of the material we had. So someone in the chat asked if this was the typical speed of a class at Berkeley. That definitely varies a lot by class. So I think that it's like really hard to tell, and it depends a lot on the level of the class. I've known professors that go extremely slow for the first 2 months, and then the third month they decide that they haven't covered anything, and then it's like the speed of light. So it can be pretty variable. Which is why it's good to be prepared. So what we're going to do this weekend is actually also send everyone a survey to get a gauge on how fast chemistry prep is going. We want to know if this is slow, if this is too fast, and what you guys so far like and don't like, just so that we can improve the class for the remaining 2 weeks. So we'd really appreciate if everyone filled out that survey as quickly as possible, just so, because that will give us more time to design the course to better fit everyone's interests. And then we'll continue giving feedback on homework. So homework 1 feedback came out last night, so we'll get 2 and 3 out to you today, and then the rest over the weekend as well. But yeah, definitely please take that survey, because we can't read minds, so that's kind of the only way we know how everyone feels.
One thing about the homework feedback, we're giving the feedback in like comments on B courses. But I think that if you comment back, we don't get notified, so we might not notice. So if you do have like a follow-up question, just email us, talk to the tutors, just like don't comment back on that homework just because we won't see it, and then we won't answer your question, and then you'll be sad.
Yeah, that's a really good point, that the feedback is better as a one direction. B course isn't really set up for conversations like that, but we also have that discussion tab in B courses, so you can also post questions there or email any of us, any of the tutors. So someone asked, how do you know if 2 elements have ionic or covalent bonds? So that depends on the nature of the elements. So for example, carbon and hydrogen, those are never going to form ionic bonds. But then if you have like sodium, which really wants to be a positive charge, then that is really likely to form an ionic compound. So we don't necessarily expect everyone to be able to look at every single element on the periodic table and identify what different types of bonds it would form. We just expect you to kind of understand generally the differences and then some of the trends. For example, sodium and chlorine keep coming up again and again as examples, and that's because all of the elements in those columns of the periodic table also behave that way. So we expect you to know that those often form ionic compounds, but we don't expect you to be a dictionary of what all of the various transition metals do. There's like over 100 elements, but we just expect sort of some of this understanding of main group element chemistry. But feel free to talk to us about that after class too. Okay, so now we're going to go ahead and end the breakout rooms and pull everyone back into the main Zoom for our office hours. But yeah, keep an eye out for that survey, and otherwise have a great weekend. I hope you enjoyed your first week of prep, especially prep chemistry. So, all right.
Don't pause it here because it has to catch up.
Yeah. probably, I didn't count.